Okay, here we have a redox equation, but it hasn't been balanced. So we don't know if our elements are balanced, and we certainly don't know if our charges are balanced. So we have to have a look at where our electrons have gone from and where they're headed to. So the first step in something like this is to assign oxidation numbers. So I'd be having a look here. This solid here, arsenious oxide, pretty safe bet with oxygen. This is almost always going to be -2. Which then we've got 6 of those. So that takes us to an overall charge of -12, which means that this arsenic over here will have to be +12 between the 4 of them because our overall compound is neutral. So if we've got 12 plus 12 and we divide it by the 4, we can see we've got an oxidation number of +3. And then over here, we've got a manganate ion. This one, again, our oxygen, -2. And we've got 4 of them, so that takes us to -8. Now, this time, this is the whole thing. The compound is an ion. So we need to get this whole thing, give it an overall charge of -1. So if we're down at -8, the difference here is to make this manganese +7. Over here, we've got an arsenate ion that's aqueous in solution, so soluble in water. Our oxygen, that hasn't changed, -2. And we've got 4 of them, so we're down to -8. But our overall charge of our ion here is 3-. So, of course, our difference between -8 and -3, this one's going to be +5. And then over here, this one's pretty obvious because it's only made of one element and it's got a charge as an ion. So the manganese ion is just +2. Notice that we write the charge of the ion as 2+, but the oxidation number is +2. Okay, so we've had a look here what's going on. So none of our oxygen's changing, oxidation state, but we can see a change in the arsenic and we can see a change in the manganese. So we should identify which one's oxidation and which one's reduction. So let's... might pick a color. Let's go here. The arsenic's gone from +3 to +5. So from here to here. We've had our oxidation number has gone up. It's increased here, so it's become more oxidized. Or another way of thinking about that is it's lost electrons, and oxidation is loss of electrons. So that's our oxidation step. And as you might expect, because you don't have one without the other, but just in case to be sure, in our manganate ion here, our manganese has gone from +7 to +2. So its oxidation state has been reduced, or we can say that it's gained electrons, which is reduction. So that one's over here. We might try to keep these sort of a bit color-coded to keep track of them. Okay, so we've identified the 2 parts of our redox equation, but straight away, hopefully, you can see that we've got a lot of this arsenic here. One of these manganese, these numbers don't look like they're kind of matching up. So the number of electrons being transferred here, being lost in oxidation, is not equivalent to the numbers of electrons being gained in this reduction. So we're going to have to balance this equation by looking at each half individually. So let's write our oxidation step first. So let's have a look then. We've got this one over here. So let's write this lovely arsenious oxide. So we might put, let's put a little oxidation over here. So we've got that one. And we know that we're going to, might leave a bit of space. We know that we're going to make this compound over here, the arsenate. Although just from your sort of stoichiometry and things that you already know about balancing equations, you can probably already see that we've got to do something with this to balance the number of atoms we've got on each side. So if this is here AS4, we're going to need 4 out the front, 4 moles here. Now, the oxygen is a bit of a tricky one. what you'll notice with redox reactions is that most of them take place in solution. So we tend not to add oxygen gas if we need to balance oxygen. Instead, we tend to split or make water. So here where I've got 6 oxygen atoms, and here where I've got 4 lots of 4, I've got 16, I've got a difference of 10. I'm actually going to put 10 moles of water in here. So that's where I'm getting my 10 extra oxygens. And I can do this because it's happening in solution. But that's liquid. Then, of course, I've introduced some hydrogen. So to balance that, the next thing I can do is to put some hydrogen ions on this side of the equation. So if I've got 10 moles of water with a hydrogen in a ratio of 2 here, I'm going to have 20 hydrogen ions here. Now, the thing about being a redox half equation, let's go for a bright orange, is the electrons. So what have we got here? We've gone from +3, this is our key thing over here, and 4 of them, to here, 4 of those, and +5. Okay, so to get from +3 to +5, the arsenic must have lost 2 electrons, and then we have 4 of them. So 2 lots, 4. We have 8 electrons. Now we write it on this side because the electrons have come from this compound. They've been lost from it. And so this is what this is sort of being produced in this reaction. And these are kind of the electrons that are left over, if you like. These are the ones that are leaving the scene. So they've started off over here. We don't write the electrons here because they're incorporated in this compound, and they've actually come out by leaving. So that's why they're over here on this side. So this is called a half equation, where we're only looking at half the picture of the redox. So just oxidation and reduction separately. So this now is balanced for the chemical species that we have here, and we've identified the electrons that we're dealing with. So the reduction equation, so for the reduction, we're starting with the manganate ion, and it's this kind of color. It's a nice purple solution, that one. Now, again, I might sort of leave a bit of a gap so I've got room to fill in and balance it. And that's become this iron, this manganese over here, which is no longer purple, but we'll keep going with this. And again, if we want to, we can see here that we've actually got oxygen on one side, so we're going to need to put some over this side of the equation. That because this is happening in solution, the source of our oxygen to balance this is in fact the water, the aqueous part. So 4 oxygens, 4 waters. And then hydrogen, because I'm now including hydrogen in my equation, I need to put that over here. 4 times 2, 8 hydrogen ions. Now the electrons in this case, this one went from +7 to +2. I'm sorry, bashing into my phone there. So here we can see, and we've just got the one of them. For it to get from +7 to +2, this must have picked up 5 electrons to reduce its positive charge down to 2 from 7, and it's gained 5 electrons. So we put them on the left side of the equation this time because we need, this is like an ingredient. We have to include 5 electrons with this to make them this species over here. Okay, so we have 2 half equations that are looking pretty good at this point. Now, I'll just take this opportunity to point out as well, this thing here about having these hydrogen ions. The reason that this is possible, why we can sort of include these or use them to balance our equation, is because we put these redox reactions to make sure that they can occur. We often put them in acidic solutions. So the environment we put them in is acidic, because hopefully you remember that your like Bronsted-Lowry, check there's a bit of that, definitions there. Our Bronsted-Lowry definition of acids and bases is that acids are hydrogen donors. So if we have this taking place with an acid that's also present, so we have a source or a kind of reservoir, like a bank of hydrogen ions available to us so that our equation can be balanced. And of course, we also have vast excess of water molecules as well, so that they can take part if need be. So that's what's allowing us to balance these redox reactions, the fact that they're actually taking place in watery acidic solutions. Okay, what we're looking at now is going, well, can we combine this information, these two halves of the equation, the oxidation and the reduction, can we put them together? And of course, the big thing here, the electrons, these don't match. So on its own, this is not viable. We actually need to have an exchange of the same number of electrons. So much like when we balance other equations stoichiometrically, we look for the lowest common factor of the electrons here. So let's pop maybe, I don't know, need some more colors. Lowest common multiple, what am I saying? Not highest common factor, lowest common, let's remember my year 7 maths. Lowest common multiple of 8 and 5. So we're going for 40, going pretty big here. But it just means what we can do, and this always works anyway, when you're dealing with multiples, it just might not be the lowest one, is we take this whole oxidation step here and multiply it all by 5. And then we take the whole reduction step and multiply that by 8. And then we know we're going to end up with 40 electrons in both, and they can then cancel each other out and we can complete our equation. So let's do it. Let's take, I might just put kind of a box around that one so we can keep track. This one we're doing times 5. And then I'm running short of colors now. I'm going to end up with some ugly browns or something in a minute. And this one, our reduction, we will do multiplied by 8. Okay, so let's write them out. I hope that I end up with enough space for all of it at the end. Okay, so the oxidation part, in fact, what I will do is I will write the whole equation. I will just color code where it's come from. So let's take, here we go, all of the things that are on the left-hand side of both half equations. Everything that's a reactant over here on the left-hand side. So we will pop our arsenious oxide over here. So we've got that straight from there. But of course, remember, everything in blue is being multiplied by 5. So let's put a 5 out the front. And then water, so 5 lots of 10, we've got 50. And then we need to keep collecting the things that are on the left-hand side. So let's just keep track of what they were. These are the things in purple now. These are the things that need to be multiplied by 8. Where was I? So plus 8 of the manganate. And 8 lots of 8. 64 hydrogen ions. And let's pop, I'm just going to keep on my electrons in orange, but 5 times 8, we have now our 40 electrons. And I might have to finish my products part of the equation underneath. So now I'm going to do all the right-hand side of my reaction down here. So the things in blue from the oxidation step, 4 times 5. So I'm going to have here I'll put down here 20 arsenate ions over here. And 20 times 5 and 100. Picked a big one, didn't I? Hydrogen ions. And my 40 electrons. So this was my aim all along, to make those match. Let's go back to this one, the right-hand side or product side of my reduction equation. I need 8 of those. And 4 lots of 8, 32 of those. Remember your times tables when you're doing this. Okay, hopefully, is that all still in view? I hope so. Okay, now we are at the point of doing some cross-cancelling. So obviously, our electrons are the first thing to go, because once they're balanced, we don't need to include them, and that is the point. The whole purpose was checking that in our redox reaction, we had an equal transfer of electrons lost and electrons gained. So that one we've achieved successfully. Now, of course, this is a bit like collecting like terms. We go through and have a look and be like, well, actually we used water and hydrogen ions to balance both of our equations. So they actually appear on both sides. So let's go through and sort of cross cancel what we don't need. So here, for example, I've got 50 moles of water here, and I've got 32. So I can get rid of this whole thing here, and instead of 50, I'll now have 18. And then I can go along and have a look and go, okay, these hydrogen ions, I've got 64 here and 100. So let's get rid of all 64 of them here. And if we take 64 away from 100, we get 36. And everything else stays put. So once we've made a nice kind of hash of that one over here, yeah, we are. We're going to have to go brown. Sorry, I've got nothing left. Okay, so let's write out our whole equation, which is our complete balanced redox equation. So these separate pieces of half equations, and we need to work them out first because we need to balance the elements and determine how many electrons are being exchanged. And then we need to put them together and cancel out, cross-cancel everything to get a complete redox equation. So we get, yeah, it's unattractive. Okay, we've still got 5 arsenious oxide. We have now just 18 water. We have 8 manganate, often combined with things in 1-to-1 ratio of permanganate, like potassium, sodium, permanganate. Don't need to write the hydrogen ions anymore. We've got rid of all 64 of them. Don't need to write the electrons. Here we go, our arsenate ion. We have a whopping 20 of those. You don't usually get one quite this large. You have to do for an exam. 36 hydrogen ions. If you do this one, you can probably do them all. Ignore the electrons now, they're dealt with. And now 8, and isn't that lucky? I've just got room. Our manganese ions, and of course our 32 water was cancelled out with this one. So here we have it. This is our final balanced redox equation. How does it compare to what we've got at the start? So we've had to multiply some of these things to make sure the electron exchange is balanced. And we've also had to include some water and hydrogen ions so that our elements are balanced as well, because otherwise we had an imbalance of the amount of oxygen going on here. So this has allowed us to balance both mass and elements and charge, quite crucially for redox. And this is it's our complete redox equation worked out by breaking up, finding where the electron exchange is happening, identifying our steps of oxidation and reduction, writing each one as a half equation, balancing them for the elements, checking how many electrons we had on each side, multiplying each whole half equation to be able to get the same amount of electrons matching, putting that together, cancelling out what we don't need to repeat and getting rid of the electrons.